Hello, this is Mr. White, and this video is on volumes of revolution, disk and washer method, part 1. Here are the 3 exercises for today, and let me comment briefly on what's going to distinguish these 3 exercises from each other. The first one will be a fairly straightforward application of what's called the disk method, and in that case we'll be revolving our function around the x-axis. The second exercise also will involve revolving functions around the x-axis, but this time the resulting solid will have a big hole through the middle of it, so it will necessitate evolving the disk method into something called the washer method. And the third one's going to go back to the disk method. The solid will not have a hole through the middle of it, but we will be revolving around an axis other than the x-axis. Now, what I don't cover in this video is a combination of washer method and revolving around a line other than the x-axis. That will be covered in the next video. Nor do I get into revolving functions around vertical axes like the y-axis. That will also be covered in the next video. Okay, so let's get to this. Here we are to take the region bounded by f of x and g of x, these 2 equations, and revolve them about the indicated line, which is the x-axis in this case. And I added this extra little condition in here. Let's look at the region in quadrant 1 only. So what does all this mean? Well, we're not going to have much of an idea until we get a good mental image, or even better, an image written on our papers. Let's start with f of x, and let's focus on the basic parabola, x squared. Okay, this minus or negative in front of the x squared tells us to flip it across the x-axis. And then adding this 4 in front tells us to translate up 4 units. So there's our f of x. And g of x is even easier. G of x equals 0. That's just a horizontal line right on top of the x-axis. Now, at first glance, it may look like the region that we're interested in is all this region here. But remember, we were told to focus only on the quadrant 1. So I'm going to trim back our sketch just to the area that we're interested in. Okay, there it is. Now make sure you recognize that the x-axis up here was serving as the boundary to this region that we see on the screen. But in this separate statement over here, this is where we're being told to now take that region and revolve it, rotate it around the x-axis as well. Let's envision what that's going to look like. Let's focus on, let's say, this first little stretch right here. This little sliver, which we'll say has an infinitesimal width or thickness of dx. If we rotate that around the x-axis, we'll get something that looks like this. And if it helps you visualize a little better, I'll pull this off to the side so you see it's just a very thin little disk. Let's say I bring a few more representative disks onto the screen, and then I drag those into place. That one would go right about there, and then this one would stack on top of it, and this one would stack on top of it. So as you may have already seen in the video on volumes of solids with known cross-sectional areas, we're going to envision these volumes as infinitesimally thick disks stacked on top of each other. And I'll remind you that these distances represent the radii of those disks. So let's take one of those disks, drag it over here, and if I want to find the volume of that one infinitesimal disk, I need to take its radius, we'll call that big R, and I need to calculate the area, pi r squared, that's the area of the face of this disk, and I need to multiply that area times this infinitesimal thickness dx. That will give me the volume. So I'll put volume of just that one individual disk as pi r squared times dx. Now, if I want to find the total volume, if I want to add up the volume of all those disks, I need to recognize that the radius of each disk varies. So we need to write that r as a function of x. That acknowledges that all these disks over here to the left have different radii that change as you move along the x-axis. And then we put the definite integral. And remember, that definite integral is an elongated s. It stands for sum. and it's the sum of all the disks between x values of a and b. That's what's going to give us total volume. So this formula right here, we're not done with this problem, but this formula right here, I'll put a box around it because that's the formula for the disk method. And we use it anytime we're adding up or stacking up an infinite number of infinitesimal disks. So let's apply it to this problem now. And when we look at all those little line segments that represented the radii of those disks, we notice that their lengths are determined by f of x. So for this particular exercise, r of x and f of x are the same thing. They are exactly equal to each other. So when we write our integral, we'll do pi, and then we'll plug in this f of x, put it in parentheses, square it, followed by dx. And I'll just write v here. I won't include the total subscript, but that is to be understood to be the total volume. Okay, we look at our sketch and we see that we are integrating from x values between 0 and 2. So those will become our limits of integration. And definitely pause, let this sink in if you need to, because at this point, evaluating the integral will be pretty straightforward. So I'm going to speed up a little bit. And I should point out that we've satisfied part 1 of this request. We're asked to set up the integral that gives us the volume. And sometimes that's all you'll be asked to do. You won't even be asked to evaluate it. So make sure you read the instructions carefully and see if you're actually expected to go on and evaluate it as well. All right, let's continue. Notice we don't have the option of unchain ruling this because the derivative of the inside function here is going to be negative 2x, and I don't have any x's hanging out beside it. So we can't unchain this. We really have no choice but to FOIL it out. So let me start over here at the left. And I'm going to bring this pi to the outside. So we'll put pi, definite integral from 0 to 2, and let's FOIL out this 4 minus x squared quantity squared. That's going to give us 16 minus 8x squared plus x to the 4th dx. Let's antiderive. And just personal preference, I'd prefer to antiderive from highest degree to lowest degree. So we'll put 1/5 x to the 5th power minus 8/3 x to the 3rd power plus 16x. Evaluate from 0 to 2 multiplied by pi. And that's going to give us, let's see, 32 fifths. I'm just plugging in the 2 here, minus 64 thirds, and then plus 32. And from that, we're going to subtract whatever we get when we plug in 0. Now we look closely and ensure that this is one of those cases where when you plug in 0, you do get 0 as an output. So 0. And quantity multiplied by pi. And that expression, if we simplify it, gives us 256 over 15 times pi. All right, that is our final volume. Okay, not too bad, right? In our next exercise, we're going to build on this concept. We're going to build on the disk method and come up with something called the washer method. This exercise has pretty much the same instructions as the last. Find the region between f of x and g of x and revolve that region around the indicated line, which once again is the x-axis. So once again, we need to come up with the sketch. And for f of x, I prefer to rewrite it in vertex form. Recall that that's where it's something like completing the square. You ignore this constant at first, and you ask yourself, what constant should I have there to make this a perfect square trinomial? Well, x squared minus 4x plus 4 is a perfect square trinomial because it could be factored into x minus 2 times another x minus 2. But then I remind myself, okay, we didn't want just plus 4, we wanted plus 5. So I'll tack on another plus 1 here to make everything equal. And that means I still have a plus 1 to tag onto this line. So what did that do for us? It allows us to envision our function as a translation of our basic parabola. So here's our basic quadratic going through the origin with vertex at the origin, and we'll move it over 2 and to the right, and then up 1. And there's our f of x. Now g of x, 2x, it's a line through the origin with a slope of 2. Not the straightest line I've ever drawn, but you know what? It'll suffice for what we're doing here. And I would point out that I've drawn my sketch carefully enough on graph paper here, such that I can even see my limits of integration. I can see that the region I'm interested in is this region right here, and I notice that that region starts at an x value of 1 and ends at an x value of 5. So a carefully drawn sketch can pay off in that way sometimes, but I'll trust you also could come to the same conclusion if you set this f of x equal to g of x and solved. Now, let's give some thought as to what this region is going to look like when we revolve it about the x-axis. Like I did in the last exercise, I'm going to trim these curves back to just the portions of the curve that we're interested in. Let's first observe that g of x is the one that's farther away from the axis of revolution, from the x-axis. This is going to be the farther away, the outer surface, and then the f of x is going to be the inner surface. I'm already alluding to the fact that this solid is going to have a big hole through the middle of it, like a donut. So let's focus on g of x. Let me bring this block up here to block out the f of x. And let's just focus on that green g of x curve. When it gets revolved around the x-axis, we're going to get some big, what's technically called a truncated cone. It's a big shape, a big solid that looks something like this. And if I were to find the volume of just that solid, ignoring the f of x, I would use the same disk method that we used in the last exercise. So volume equals the definite integral from a to b pi r of x squared dx. Now in this case, the radius is determined by g of x itself. Notice that all these radii I'm drawing over here to the left have lengths determined by the g of x equation. And again, our limits of integration, a and b, are 1 and 5. So this integral becomes the integral from 1 to 5 pi, and for big R, we'll put in g of x, which is 2x quantity squared dx. Okay, I'm going to trust that you got that down pretty well. And just to save some screen space, let me move that out of the way and move this up here. Okay, let's now think of how our f of x equation is going to affect this volume. I'll reveal it back on the graph. And just in the same way that I imagine g of x revolving around the x-axis, I can imagine that it crossing back into the plane here. So I've basically here just drawn the profile of this solid shape. Oops, you may have noticed I had that drawing off a little bit. It's corrected now. But anyway, I could do a similar thing with f of x and draw its profile. And then envision the three-dimensional shape that it is cutting out of the g of x shape. Not always easy drawing these 3D shapes. I'm trusting some of you will sympathize with my plight here. And we'll pull this volume off to the side. There, I bought a little extra room. So here's what we need to be envisioning. We start with this outer shape, this green shape is a big block solid, and then this red shape represents the volume that is getting cut away or removed from the green shape. And that's why we have this big hole, this big opening between the two halves of the profile. So if you buy this premise that we need a green volume minus the red volume, we can imagine some subtraction. I'll put a little minus sign right there. Then we also need to subtract the volume representing that red volume. So let's write its definite integral in a similar manner to how we did for g of x. It's still the same limits of integration from 1 to 5. It's still pi times radius squared dx, but this time the radius will be given by the f of x function, x squared minus 4x plus 5. If that all made sense to you, then congratulate yourself because we've completed the setup. And that is definitely the hardest part of this process. So this is where you pause, think about it, take a break if you need to. I'm going to go ahead and evaluate these two integrals rather quickly. Okay, so let's start by saying v equals integral from 1 to 5. Let's bring this pi to the outside, and then the 2x quantity squared will become 4x squared without parentheses on the inside. But rather than close off with a dx, how about we go ahead and combine both of these integrals into one? They have the same limits of integration, 1 to 5, 1 to 5, and they both have a pi that can be taken to the outside. So let's subtract the x squared minus 4x plus 5 quantity squared dx. And if we FOIL out that ugly trinomial squared and then distribute the negative, we get this. Ah, beautiful. Aren't you glad I did that for you? And if I combine these two like terms and then antiderive, we get this. And if we plug in 5, we would get 250 over 3. And if we then plug in 1, we'd get minus negative 158 over 15. I would tell you I was doing this all in my head, but I'm afraid you wouldn't believe me. And that all equals, deep breath, 1408 pi over 15. Wow. Realistically, on tests or on the AP exam, this is the type where you probably would have been asked to just stop after setting up the integrals, and you'd be thankful for that. Okay, let's really contrast. Before we go on to the last exercise, let's point out that in this integral, we had a function squared minus another function squared. And we've probably seen a similar formula in the book, and hopefully you understand where it came from and how it makes sense now. Let's go on to the last exercise and see how this pattern contrasts with that one. One more time, similar premise. We're revolving a region between two curves around an axis. Still have our f of x, still have our g of x. But notice this time that our axis is not the x-axis anymore. It's a horizontal line parallel to the x-axis, but 9 units above it. So rather than pull out some graph paper onto the screen, I'm just going to freehand this, perhaps a risky move. For our f of x, we know that x to the fourth looks kind of similar to a parabola, but it's got a little bit more of a flat nose. It still goes through the origin. Now the negative in front will still flip it across the x-axis. And adding the 25 will still move it up, translate it up 25 units. Okay, there we go. And we'll now turn our attention to g of x. G of x equals 9. That's just going to be a horizontal line 9 units above the x-axis. So this is the region that we're interested in. And that region starts at this value, which we'll call A, and this value, which we'll call B. Notice those are not the same things as the x-intercepts of f of x. They're probably close, but they're not the same thing. So let's trim this back. Now, since I'm only sketching this roughly, and I didn't draw it real carefully on a grid or on a graph paper, I don't know what A and B are, but I can find them out. I can set f of x equal to g of x and solve, and that will give me my A and B values. Turned out to be very neat and convenient in this case. So we know A is -2 and B is +2. Okay, I trust that all made sense. I'm going to get rid of some of this just to reduce screen clutter. Okay, let's pause and imagine how this would look if instead of being revolved around this horizontal line, y = 9, what if it was being revolved around the x-axis? Well, this would basically be very similar to what we did in the last exercise, where we thought of an outer shape and an inner shape, and outer volume minus an inner volume. And we had the solid in the end with a big hole right through the middle of it. Here's the big hole through the middle of the shape. And that's what gave us a formula in this format. And I'm just realizing now that I never really explained in the video why that's called the washer method, but hopefully we've gone over that in class, at least. Any case, keep this in mind. I'm going to put this off to the side again, and we'll contrast what we actually get now when we look at the original problem, which said we should be revolving around a horizontal line, y = 9. Yes, we need to be revolving around this line, which, yes, that is the same as our g of x, and that's why we won't have a hole running through it. So the horizontal line, 9 units above the x-axis, will not only serve as the border of our region, but it will also serve as the axis that we revolve around. Okay, so again, revolving that shape around this line will give us a profile for the red curve at least, the f of x. It's going to come down and do something kind of like this. Okay, there, my first attempt wasn't very good. Now, what about the g of x? What about the inner surface, so to speak? Again, notice that g of x is right here. It's lying right on top of the axis of revolution, so it's not really going to create any inner radius or any inner surface. That's why we're going back to thinking this as the disk method rather than the washer method, because there's no hole going through this part. Okay, here are the corresponding line segments representing the mirrored profile. And since we're back to thinking of these as disks again, we need to look very carefully about the radius of each disk. Okay, so I just drew a disk for this arbitrary point. Let's drag this off to the side. And as you ask, what is the radius of that disk there? What is that r of x? Notice that r of x is no longer the distance from a point on f of x all the way down to the x-axis. It's not that long anymore. It's the distance between f of x and g of x. That difference between f and g is r of x. And you can even write, at this point, if you like, r of x equals f of x minus g of x. And since there is no longer any outer surface versus inner surface, we're just dealing with disks, not washes anymore, we'll go back to the formula volume is pi r of x squared dx. And in this case, r of x has been replaced by f of x minus g of x. So this is a big distinction. Let's compare it with that washer method that we saw in the last exercise. These formulas are so similar, and it's understandable why every year many students get them mixed up. So take a moment and study it. Make sure that you completely understand the difference between the washer method, where we're revolving two shapes around the x-axis. We've got an inner surface and outer surface, and inner radius and outer radius. That's when we have the f of x squared minus g of x squared, versus this disk method, which we're about to implement here in this example. That's where you have f of x minus g of x, and then the quantity is squared. Big difference. That is for when we are revolving disks about a horizontal line that just happens to be given by the equation g of x. All right, let's take some of this off the screen and use this disk method on our exercise. So I'll remind you, here are the f of x and g of x equations, and our formula becomes volume equals the integral pi out in front, f of x, or 25 minus x to the fourth, minus g of x, which is just 9. And recall that up here we had earlier calculated our limits of integration as -2 and 2. So we'll put from -2 to 2. All right, we'll notice that that gives us, let's see, the 25 minus 9 will give us 16 minus x to the fourth squared. And if I FOIL that out, we'll get 256 minus 32x to the fourth plus x to the 8. We'll antiderive that and get this from -2 to 2 with a pi multiplied outside. Plugging in the 2 gives us this beast of a fraction, and plugging in -2 gives us its opposite, all times pi. So our final volume is 32768 pi all over 45. And that, ladies and gentlemen, concludes our video. I hope you had as much fun as I did.